Let's plan a lab using a ramp so we can measure acceleration. We would like to determine the car's acceleration down the ramp when it is released from rest. What measurements do you need to make? What do you need to make them well? What do you need to do the calculations? We'll show one way to find acceleration. You might find another that's equally good. But for now, we're going to make a measurement of T ramp. That will be the time that the rear wheels of the car get to the bottom of the ramp. So you specify rear wheels. So for example, you don't measure where the rear wheel takes off here, and then at the bottom, you measure when the front wheel hits. That would give too short of a time. So you got to time the rear wheels. Then measure time on the table, which again will measure the rear wheels from the bottom of the ramp right here until it reaches a point 2 meters away. So there's the rear wheels. So the front of the car will actually be beyond the 2 meters, but the rear wheels would be right at 2 meters. And so our delta X table will be 2 meters, and time table will be whatever we measure. What do you need to make the measurements? Well, we want to measure time in 2 places. So for that, we can use a stopwatch or your cell phone. We need to measure 2 meters, so we'll use a meter stick. We will need to do some calculations based on our measurements. So the first measurement, we measured T table, the time from the bottom of the ramp to point P. We will want to find the final velocity. Now we're going to assume that the velocity stays constant from the bottom of the ramp to point P and equals VF. See how these are the same? VF, VF. We're assuming no friction on the horizontal plane there. And of course there is, but we're not going to worry about it for this particular experiment. And from that, from velocity and time, we can find A. Do you remember how to do that? Well, this is how we'll find acceleration. We're going to calculate the final velocity by taking the distance delta x, this distance here. We know that's 2 meters. And then we want to find the time it took to go that distance. And of course, hopefully we measured that. That's T sub table. So then we will divide the displacement 2 meters by T sub table. That will give us the final velocity. So when we go to our acceleration equation, what was our initial velocity? Well, that's up here, 0. And we will find the time it took to go from a 0 velocity here to a final velocity at the bottom of the ramp. And which time measurement do we use there? T ramp. So this experiment and work we've done previous enables us to find the acceleration of an object if we are given either its initial velocity and its final velocity, or just the change in velocity delta v, because delta v is vf minus vi, and then the time it took to accelerate from vi to vf. Sometimes we need to find one of the quantities, delta v or t, when we know the acceleration and the other quantity. Sometimes we need to find vi or vf. We need to use algebra. We need our rules. Hopefully these rules will be familiar to you. These are what we used in the constant speed unit. To undo a mathematical operation, you must do the opposite. Okay, so if you had division, you would have to do multiplication to undo it. You can do anything you want except divide by 0 to one side of equation, as long as you do the same thing to the other. And then, if there's more than one operation going on, undo them in the opposite order in which you would do them. This is the opposite of the order of operations, or maybe you'll learn that as PEMDAS or PEMDAS. And you can always switch the left and right sides of an equation. No restrictions on that. Let's work an example. We have our equation, our definition for acceleration, which is delta v over t, and we'd like to solve for delta v. We want delta v all by itself on the left. First thing, we undo delta v divided by t by multiplying it by t. And if we multiply the right side by t, we have to multiply the left side by t. So that's using rules 1 and 2. We now have at equals delta v. And we like delta v on the left because it looks neater, so we just switch the sides, which is rule 4. This formula here now gives us the change in velocity given the time and acceleration. Let's step through a solution now. We have a car that accelerates at 4.5 meters per second squared for 8 seconds. What was the car's change in velocity? If you'd like, please use the template down here. Give it a shot on your own before you go to the next slide. First, we find the givens. So here's our acceleration, and that goes there, 4.5 meters per second squared. Then we have a time, 8 seconds, that follows that line. And we want to find change in velocity, which is delta V. We then draw a diagram. Here's our cart. It accelerates at 4.5 meters per second squared for a period of 8 seconds. Then we take our formula. So now we have a couple of formulas, right? We had speed is distance over time, velocity is displacement over time. Now we have acceleration, which is change in velocity over time. We want to find change in velocity, and our equation has acceleration on the left side. We move it up here to the manipulate box, and then we want to isolate delta V. We want to undo the division by t, so we multiply by t. Then we have to do that to the other side also, so we have a times t. That's what we have here. And then we switch it, so delta V is on the left-hand side. Then finally, we put our equation down here, and we substitute in our numbers. 4.5 meters per second squared times 8 seconds equals 36 meters per second. And you can see here these units. This second cancels out one of these, so the units are proper. Then we rewrite it over here. Delta V is 36 meters per second.